Welcome to Lesson 2 of Non-Euclidean Geometry. We're going to talk about Euclid's parallel postulate a little bit more. I'll give you some historical background, and we'll also introduce the Saccheri's quadrilateral, which is used to define hyperbolic geometry, which we'll do in a subsequent lesson. As noted in the previous lesson, the modification of Euclid's fifth postulate leads to alternate geometries such as the hyperbolic and elliptic geometries, which we'll talk about later. Before proceeding to discuss the alternate geometries, let's explore Euclid's fifth postulate a bit more. This, what I have listed down here is the actual translation from, I assume, Greek into English. It's not stated as I mentioned in the previous slide. This is the actual statement. And there's many equivalents to this, which we'll talk about. So let's look at this. If a line segment intersects two straight lines, forming two interior angles on the same side that are less than two right angles, in other words, less than 180 degrees, then the two lines, if extended indefinitely, meet on that side in which the angles sum to less than two right angles. Sorry, it's quite a mouthful here, but I have a picture of it on the next slide, which will help us visualize what's being stated here. So here's a picture of what I read off from the last page concerning Euclid's parallel postulate. So these are the two lines. He's talking about L and M, and then there's a third line, N, that intersects these two lines. And he's saying if these two interior angles, alpha and beta, are less than 180 degrees, or in his words, less than two right angles, then the lines on this side where we have these two angles that add up to a less than 180, the two lines will intersect. So kind of obvious if you know geometry that these lines would intersect here. And what he doesn't say, but it's implied that the lines on the opposite side just diverge and get further and further apart. Okay, so that's the statement of the fifth postulate. And what we'll do for hyperbolic and elliptic geometry is actually negate that postulate and then fill in something in place of it. And from there we'll get an axiomatic definition of these alternate geometries. In the next few slides, I want to talk about the equivalent statements to Euclid's fifth postulate. We already saw one, that was called Playfair's postulate. Given a line and a point not on the line, there's exactly one line through the point and parallel to the given line. That's often used as a substitute for the fifth postulate because it's kind of easy to understand. The next one, the sum of the angles in every triangle is 180 degrees. That's called the triangle postulate. Then that's in turn equivalent to there exists a triangle whose angles add up to 180 degrees. The sum of the angles is the same for every triangle. And that's not true in some non-Euclidean geometries, as we'll see. The statements on this slide are also equivalent to the parallel postulate. The first one is there exists a pair of similar but not congruent triangles. Remember from high school geometry that congruent means the figures, in this case the triangles, are exactly the same. Their angles are the same and the length of their sides are the same. Similar just means that you have the same angles, but the sides are basically a multiple of the other. So you may have side lengths of 1 for one triangle and 10 for the other, and their angles are all 60 degrees, just as an example. So they would be similar. Then the second one, every triangle can be circumcised by a circle. That just means a circle will exactly touch the three vertices of the triangle, and that's always possible. Or in other words, the three vertices of a triangle determine a circle. If three angles of a quadrilateral are right angles, a quadrilateral is a four-sided figure, then the fourth angle is a right angle. There exists a quadrilateral in which all angles are right angles. Such a quadrilateral is known as a rectangle, and a square would be a special case. And then the last one on this slide, there exists a pair of straight lines that are at a constant distance from each other, basically parallel lines. We have even more equivalents to the parallel postulate, and this is only a partial list, so bear with me. This is the last slide on this. Two lines that are parallel to the same line are also parallel to each other. So that's just transitivity. In a right triangle, in other words, a triangle with a right angle, the square of the hypotenuse equals the sum of the squares of the other two sides. That's the well-known Pythagorean theorem. The law of cosines holds true, which this is a generalization of the Pythagorean theorem where you don't have a right angle, or you don't necessarily have a right angle. And this 7 is from my book, which I mentioned in the first lesson. You can download that freely, and I believe that's probably just a reference to the Wikipedia article on this topic, in case you're interested in the law of cosines. There is no upper limit to the area of a triangle. This is not true for some of the other geometries, which is a bit surprising. The summit angles of the Saccheri quadrilateral, I believe this is the reference to the Wikipedia article, are right angles. We'll see this in this lecture, actually. This is an important concept, so you don't really know what this is yet, but we'll get to this in a minute. If a line intersects one of two parallel lines, both of which are coplanar with the original line, then it also intersects the other. So this is one that clearly is not obvious that it's equivalent to the parallel postulate. So you can see how someone might assume this and then prove the parallel postulate and then claim victory, but then I guess someone figured out later on that that wasn't valid in the sense that you were assuming the conclusion. A Saccheri quadrilateral has two equal sides perpendicular to its base. It's named after Giovanni Girolamo Saccheri, who used it extensively in his 1733 book, Euclid Free of Every Flaw. This was an unsuccessful attempt to prove the parallel postulate using proof by contradiction. As we saw in the previous slide, one of the equivalent statements to the parallel postulate was for the Saccheri quadrilateral to have right angles for its summit angles. So let me explain what are the summit angles, and in general, what's this Saccheri quadrilateral. So we have three versions of it here. It has it's a four-sided figure. The legs AD and BC are equal in length and perpendicular to the base. That's always true. So AD and BC are perpendicular to the base and have same length in all cases. The top side, this thing here, CD, is called the summit, and the angle here at D and the angle at C are called the summit angle. So if these angles are 90 degrees, then we have an equivalence to the parallel postulate. The advantage of using the Saccheri quadrilaterals when considering the parallel postulate is they represent three mutually exclusive options. So as we saw, this first case is where we have Euclidean geometry. If the summit angles here at C and D are bigger than 180, greater than 180, then we have the elliptical geometry. You could think of this being drawn maybe on a sphere where the base is on the equator, and then this is further north, and of course the lines would bend, and then you would have an angle here bigger than 180 degrees. So the Saccheri quadrilateral having sum at angles greater than 180 degrees is equivalent to what we'll see is the elliptical or spherical geometry. And then if the sum at angles are less than 90 degrees, this picture down here on the bottom, then we have hyperbolic geometry. And we'll actually use this to define hyperbolic geometry, as you'll see in the future lesson. And this figure here comes from Wikipedia article, Saccheri quadrilateral. On the next few slides, I have a rather short history of the parallel postulate. As you can imagine, this was first posed by Euclid, probably even before Euclid, but he put it down in his multi-volume book, and that was over 2,000 years ago. So there were multiple attempts to prove this from the first four axioms, which I'll show you in the next slide, and things went on until the last few hundred years, where people realized that we could actually modify the parallel postulate and create alternate geometries. So that's what I'm going to do here. First, I'll show you the five postulates, first five postulates from Euclid, and then we'll get into a little bit of the history behind it. Okay, so here we have Euclid's postulates, and I should mention here that he wrote them in a style of construction, in the sense of you can construct this, or you can construct a right angle, or you construct the circle. So that was his manner of writing, and so that's reflected here in these postulates. First one is a straight line segment can be drawn joining any 2 points. We all know that from high school geometry. 2 points uniquely determine a line. The next two seem fairly obvious. Any straight line segment can be extended indefinitely in a straight line, or into a straight line. So we can do that. And given any straight line segment, a circle can be drawn having this segment as a radius and one endpoint as the center of the circle. Again, these seem kind of obvious. All right angles are congruent. That's almost the definition. And then we have the parallel postulate, which we already described in multiple ways. We'll take the Playfair's definition, where you have a line and a point not on the line, and there's only one line going through that point that doesn't intersect the other line. And what people tried to do was use these four to somehow prove this, and that didn't work. And that's pretty much a lot of the early history of the parallel postulate. In fact, people have noted that Euclid put off using the parallel postulate in his books, Euclid's Elements, as long as he could. He tried just using these four with other common definitions, and so that was kind of an indication that he was also uneasy about this postulate. I think I mentioned everything on this slide already. It's basically saying that people tried to prove the parallel postulate from Euclid's first four postulates. All attempts were unsuccessful. Eventually people realized that it was truly a postulate, not something that could be proven, and in addition, mathematicians realized that you could modify that fifth postulate and get non-Euclidean geometries, which is really the topic of this series of lessons. One other point, the hyperbolic geometry makes use of a good bit of what's in Euclid's Elements, Euclidean geometry, and it would be helpful to have a copy of Euclid's Elements translated into English if you're an English speaker, and I have a reference here too, but I'll actually put the link in the description of this video to a free version, a free electronic version of Euclid's elements. So I have a few historical points leading to eventually the discovery and acceptance of the elliptic and hyperbolic geometry. It turns out the time between discovery and acceptance was rather long. I guess that's maybe happens sometimes. So the first point here, let me point here, Proclus, he lived from 410 to 485 AD. He wrote some commentaries on attempted proofs to the fifth postulate from the other four, and he in particular talks about Ptolemy's false proof. Now, he was born in 100 AD, and Euclid was 300 BC, so already we're talking about quite a long history here. Proclus goes on to give his own false proof, which turned out to be the Playfair's postulate, which was later named as Playfair's postulate. So something good came out of his his erroneous attempt to prove the fifth postulate. And similar here for Ibn al-Haytham, also known as al-Hazan. He worked a bit later, and this is like another 500 years later. So he also had an attempted proof that didn't work out. But out of his work came the concepts of motion and transformation in geometry. So again, something good came out of a failed attempt. Then Nasir al-Din al-Tusi also wrote some critiques of the parallel postulate. He had his own erroneous proof of the parallel postulate, and but more notably, he also had the concepts of elliptical and hyperbolic geometry. Now he ruled them out, but his son didn't, and I'll talk about that on the next slide. Nasir al-Din's son, Sadr al-Din, also known as Suedo Tusi, authored a book on the topic in 1298 based on his father's thoughts. And he also revised the Euclidean system of postulates and theorems to align with his non-Euclidean vision of the parallel postulate. Sadr al-Din's work was published in Rome quite some time later in 1594, and that influenced some of the early European geometers such as Giordano Vitali, Girolamo Saccheri, which we talked about. His work was used with the hyperbolic geometry, and Johann Lambert. Lambert proved the non-Euclidean result that the sum of the angles in a triangle increases as the area of the triangle decreases. So this is kind of wild. We'll talk about this later, but I'm sure if you're only familiar with Euclidean geometry, this sounds pretty much off the wall, but we'll talk about this later on. In the 19th century, mathematicians more fully considered alternatives to Euclidean geometry. In this period, logically consistent non-Euclidean geometries were developed. Nikolai Ivanovich Lobachevsky and Janis Bolyai in 1829 and 1831 respectively, independently defined what we now consider to be hyperbolic geometry. So quite a long time from Euclid, who was born in 300 BC, to actually formalizing an alternative geometry is over 2,000 years. The famous and prolific mathematician Carl Friedrich Gauss also accepted the idea of non-Euclidean geometries, and he has a letter that's been translated from German to English, which I'll talk about on the next slide. But he never published his work on the topic, unfortunately. In any event, the resulting geometries from these ideas about non-Euclidean geometry were developed fully by Lobachevsky, Bernard Riemann, and Henri Poincaré into hyperbolic geometry and elliptic geometry. The independence of the parallel postulate from Euclid's other axioms was finally demonstrated by Eugenio Beltrami in 1868. Here's the letter from Gauss that I mentioned on the previous slide, translated it from German to English. He says, the assumption that the sum of the three angles, he's talking about a triangle, is less than 180 degrees leads to a curious geometry quite different from ours, meaning the Euclidean geometry, but thoroughly consistent, which I have developed to my entire satisfaction. Unfortunately, he never published this. He goes on to say that he looked for contradictions in this non-Euclidean geometry, but he was not able to find any. So unfortunately, his work on this topic did not get published, and so we don't know really the details of what he worked on. But he did accept the non-Euclidean geometry. And so that's pretty much it for this lesson. I'll get into more of the actual mathematics in the next lesson and the following lessons. So stay tuned.